This video is from the topic B2 and it's looking at the model gut, it's looking at the small intestine, and it's basically proving why we must break down our food, digest our food to enable it to go into the blood. So we talked before how starch is a long chain molecule, it's insoluble, it's a large molecule. And it's made up of these units of glucose, which are small soluble molecules. And they must be small and soluble to get through the wall of the small intestine. So this is called Visking tubing, and we're going to use it to model the small intestine. It is a partially permeable membrane. That means it's partly permeable. Some stuff will go through it, the small soluble stuff like glucose. Some stuff won't go through it, for example, the starch. That's why it's so important that we digest our food, make it smaller to enable it to get through. So what I'm going to put into this Visking tubing is some starch and then some amylase. And amylase is in that group carbohydrates. It's an example of a carbohydrate digesting enzyme. So you get plenty of the starch in there. Now that starch, in theory, is too large to get through the wall of this small intestine. I'm then going to have some of my amylase, which is my enzyme to break down that starch into glucose. I'll put a decent amount in so I get the result quite quickly. And that should take that starch, and the starch will keep entering the active site of the enzyme. And don't forget, those enzymes are reusable. So as soon as they've had some starch enter there and the bond's broken in the starch, another section of starch can enter that active site and continue the process. So I've now tied that up at the top. I'm going to cut off that bit of Visking tubing at the top there, and that is my contents of my small intestine. So starch, large insoluble molecules, and some amylase. The enzyme's ready to chop up all of that starch. I'm just going to give it a rinse in some water here to make sure I've got no starch on the outside of it. And then in my rack here I've got a boiling tube there, and I'm going to add some water to the tube, which will be surrounding the Visking tubing. Now that water represents the blood. So if I show you what I've got my tube of water representing the blood, and I've got my small intestine model inside it with the starch and the amylase. And I'm going to leave that so that the amylase has time to chop all of that starch down into those smaller units of glucose. So my model gut has been sitting there with the starch being broken down by the amylase, surrounded by the blood. The water is representing the blood. Now I'm going to do two things. I'm going to first of all check for starch. I want to see, is there any starch in the blood? So I'm going to extract some of the blood and put it into this tray. And I'm going to test using iodine solution. Now, the iodine starts off orange, and if it goes blue-black, then there is a presence of starch. I've got no colour change there at all, so that means I'm able to say starch test using iodine solution in the blood is a negative test. There's no starch present in the blood, which is exactly what we expect, because starch is too large a molecule to get through the wall of the small intestine and into the blood. That's why we need to digest it using that amylase. Next thing I'm going to do is take some of that blood and I'm going to put it into this tube, which I've labelled in the blood, and this is in some hot water because I'm going to use the Benedict solution, which is heat activated, to see if there is sugar in the blood. Now this is going to take some time, so I will pause and come back to it. Add some Benedicts to there, and we'll see what colour change we get. So that was the Benedict solution. Okay, so it's in the blood, and we've got in there Benedict solution and some of the, in inverted commas, blood. Now I need to get into the Visking tubing itself and test the contents of the Visking tubing, which is the small intestine. So this is looking at what is in the small intestine. Now we have a couple of predictions that could be made here. One, all of the amylase may have broken down all of the starch, in which case there'll be no starch present at all. Or if I haven't left it for long enough, we will see some starch. So I'm just going to give that a snip and as carefully as I can try and drain some into there. So starch may be present if the mixture has not been left for long enough and some of it hasn't been broken down by the enzymes. Equally, if it has been left for long enough and the amylase has chopped up all the starch, we will have a negative result and it will stay orange. Let's see what we've got. So there we go. Inside the small intestine, all of the starch had been broken down by the amylase. Now it would have been all right if we'd found starch in there. It just would have meant that it hadn't had time to break it all down. But in this case, it had been left for long enough and all that starch has gone. The amylase has done its job. Now the rest of the contents of the small intestine, I'm going to put into this tube. There we go. And I'm going to add some Benedicts to that, and that's going to see if there's still sugar left in the gut. And again, I'm going to leave this for a time and come back to you with the results. We now have our results from the Benedict solution sugar test, and as you can see in the blood we've got that colour change, so we've gone from blue to green, saying that yes, there is sugar in the blood. Okay, so I'm going to give that a tick, and sugar is present as it is small and soluble. Okay, it is a product of the digestion of starch. Okay, we've also got glucose in the gut. Now, if you remember back to B1, sugar will move by diffusion from the small intestine into the blood because there is a higher concentration of sugar in the small intestine than there was in the blood. Now, we get to this point where we reach an equilibrium. There's the same concentration of sugar in the blood and in the small intestine. So at that point, the body is able to use active transport, which is movement from low concentration to high concentration, to pull over all of that glucose from the small intestine and bring it to the blood. We didn't have any mitochondria in our model, so we weren't able to supply that energy for active transport to bring it across. So we just got to the point of diffusion and reaching that equilibrium where there was the same concentration of sugar in the small intestine and in the blood. So did we find sugar still in the blood? Sugar is, in the gut, is present in the gut as active transport, could not remove all of it. Okay, so let's summarise. We had a model gut with the starch and amylase solution inside the Visking tubing, which represented the small intestine. We had water around the outside, which represented the blood. And we've tested, after leaving it for some time for the amylase to chop up the starch, we've tested for the presence of starch and the presence of sugar. We found no starch in the blood. It was too large, it was insoluble, so it could not fit through the wall of the small intestine. We found no starch inside the Visking tubing because it had all been digested, broken down by the amylase. It would have been okay if we did find some starch there. It would have just meant that it hadn't been broken down yet. The sugar test, the Benedict's test, was to see had the soluble small sugar molecules made it into the blood, and yes they had. The sugar was present in the blood because it's small and soluble, and it is the product of the digestion of starch. Inside the gut we still had some sugar present because we said that initially that sugar moves across by diffusion. When we get to the equilibrium, which we definitely can see here, the rest of that sugar is pulled across into the blood by active transport, and that couldn't happen. We didn't have the energy supply, we had no mitochondria, so we couldn't pull the rest across. So that's why we found some sugar still present in the small intestine. Hope you found that useful. Thank you.